In this lecture, we're going to go ahead and take a look at models of the atom. So on this slide, what we're seeing is a variety of different images that represent the different models of our atom through history. So we start in the upper left-hand corner. That left-hand corner is referencing the plum pudding model, which we'll talk a little bit about today. That nuances into probably the Bohr model is what we'd be looking at here. This was our plum pudding. And within this system, we've got a nucleus as distinctly different, and then we have these orbits representing our electrons, which we'll talk about in a little bit. And then we move into now not atomic structure, but now electron structure, where we're looking at orbitals, and then we can actually see the mathematical solves for where these cartoon images are ultimately coming from. So as we've staged through history, we've increased our abilities to go through and understand and represent the model of an atom, which is pretty neat. So where we'll start is with Dalton. Dalton came up with his atomic theory in the early 1800s. We've got the 5 bullets of what Dalton's theory is listed out here, but I kind of want to break down some of the things that we're seeing on this page. So first and foremost, what we consider is that we've got, say, a compound or a molecule that we're looking at within nature. So what Dalton noted is that that could be decomposed through a chemical reaction. That chemical reaction then takes us into the constituent parts. So we would get a variety of different shapes that would make up, say, the sun. And so what we're looking at here is now a representation of how we can navigate our structures. Okay? If we take that a step further, Dalton went through and created what would be his periodic table. And if we're looking at this document right through the middle, it looks kind of artsy and fancy, which is kind of neat. A touch of alchemy associated with this. And really what we're talking about when we talk about his periodic table is just that upper portion is his periodic table. And you might think from our previous lecture that we had something like 118 different elements. How are we now looking at, 24-ish elements? What's that differential? Why? And a lot of that has to do with the timing of the discovery. When Dalton's looking at this in the early 1800s, he doesn't have the breadth of knowledge or the isolation, the chemical skills to isolate each of those individual elements. So all he's got to work with are the 24 he sees here. He went through and came up with symbols to associate with those, and that's the symbols that we would see. So if you're seeing a circle with a dot, that would represent this first element, which would conveniently represent hydrogen. You could then go through and look at how you could combine those symbols to make different compounds. And so our compounds, he's got a list of compounds down below. So we're looking at our compounds, which are the combination of multiple different types of elements, which we saw defined in our previous lecture. If we then shift focus and now actually look at Dalton's actual theory, we want to go through and address kind of each of those individual components associated with it as we navigate through. Just realized maybe I can trash clear ink. That's a little bit better. And we can look at each of these theories. So number 1, an element is composed of tiny, indivisible. Okay, I want to enunciate that there's a D there, not an N, or a DI, I guess we should say, for indivisible. Indivisible meaning not break apart. Okay, we can't break them apart. Not invisible, indivisible. So these are the smallest particle that we could possibly have of matter. That represents our individual elements. All atoms of an element are identical and have the exact same properties. So if I find a hydrogen atom on the moon versus on planet Earth, they're going to have the exact same characteristics and properties that I would associate with the element hydrogen. So there's no differential for individual elements. We can then move to his rule 3, if you will. Atoms of different elements will combine to form compounds, and that's where we were saying our system over here. So when we take different elements and we put them together into a chemical connection, shown here just by removing the space between the elements, we're now talking about a compound. Compounds contain atoms in small whole number ratios. So this kind of ties back to this indivisible. So if we think about the formula for water, you might know that formula for water is H2O. So what rule 4 is saying is I can't have H1O a half. Okay, so we're whole number ratios all the way through. There's no fractional elements within an individual compound. And then the last rule is that atoms can combine in more than one ratio to form different compounds. So this is a good opportunity for a little bit of a sidebar of a joke. And within our joke, we would start with 2 people walk into a bar. The first one orders a glass of H2O. And the second one orders a glass of H2O2. The second one dies. Because H2O2 is hydrogen peroxide, which is a toxic chemical which can cause paint to peel, if we want to date this video. Within that, that's now Dalton's atomic theories. What we want to do as we navigate through the rest of this lecture is think back to these theories or have them in our mind and be like, well, wait, doesn't that experiment invalidate that theory? Because that's going to be one of your test questions, is to try and recognize those differentials. So what are Dalton's theories? We got them. And then we move to kind of our question. These are potential exam questions. How are Dalton's theories disproved? So let's go ahead and see. So Dalton, as we saw here, was early 1800s. We're waiting for roughly 100 years for Thomson to come through and change the model of the atom. Thomson's model noted that there are two subatomic particles. So individual elements are made up of two smaller things. There's negatively charged things and positively charged things. And depending on the amounts of negatives and positives that you have within it, you can change the identity of the element. So that's how we would get hydrogen versus helium versus lithium, beryllium, and all of those. In his experimenting, he's discovered that an electron has a relative charge of -1, and a proton has a relative charge of +1. These are relative, meaning it's not an absolute charge. There's not a unit necessarily associated with it. We just know that the charge of an electron is equal and opposite to that of a proton. So it's a 1-for-1 match, just opposite degrees. Okay. Where I think we get a little bit of fun within our history here is that why did we need to wait to the late 1800s to actually discover this? Okay. Well, interesting phenomenon. What did we need? We actually needed a vacuum. Not the little vacuum cleaner that we run around through our house, but kind of. Okay, what we needed was a vacuum so that we could take a glass tube. This is what's known as a cathode ray tube. And so within this tube, if we try to put electrical current in it, nothing happens. Okay, but if we go through and we remove all the air from it, i.e. we connect it to a vacuum, we can't get rid of all the air, but we get rid of most of it. And now once we've gotten rid of most of it, when we pump an electric current on it, what we started to notice, or rather what Thomson started to notice, is that you would see a light beam turn. Okay, go from one end of our electron source to the other end of our electron source. So our negative would flow to our positive. Okay, and what does this mean for us? Well, this means that we have to have something smaller than our individual elements. So that would be the existence for our subatomic particles. Okay. The next thing he played around with, or maybe he just accidentally discovered at this point, I honestly don't know. But let's just say he played around and he put a magnet near it. And if we put, I know magnet is spelled a little bit differently than that. So if a magnet was put next to it, what he noticed is that he could get that beam to change directions a little bit. Okay, so what does that mean? Okay, if it's feeling the magnetic pole, what we're saying is whatever that beam is has some kind of charge associated with it. This is ultimately how we get the positive and negative charge. What he's detecting here are electrons flowing through from one end to the other. Because we now have the existence of electrons, we also necessitate the need for protons, because if we just had electrons, everything would be negatively charged and nothing would be neutral. We have clear evidence for things being neutral at this point, which means we have the existence of both negatively charged particles and positively charged particles, which is pretty cool. So within his model, now that he's got these particles, he now wants to go through and come up with some kind of explanation for how this would describe an element. And so what he came up with is that we have this C of positive charge. So these positive charges are just kind of floating around in a giant sphere. And we pick spheres because they're like balls, they bounce off of each other. Okay, it's the simplest representation for them. Okay, and then within that, he postulated that our electrons were little seeds effectively sitting in this sea of positive charge. And so what he compared this to was plum pudding. So plums are our electrons in this sea of positive charge. Okay? It's not a bad theory. We know we have negative and positives, and we know they have to exist in this roughly same space to neutralize each other out. So we now have a theory to explain this. Okay, if we're going through and looking at what things Thomson could go through and do, he could only calculate the mass to charge ratio of the proton and electron. So he could see their relative mass and their charge, but he couldn't get specifics on either of those. That required more science later on. So as we continue through, and note this experiment is not in your textbook, so this might be a careful one to pay attention to, but it's got some interesting things going on within it. We get Millikan, Fletcher, eyesight, and patience. So Robert Millikan was able to determine, or was given credit for determining the exact charge on an electron in 1911. So that exact charge is actually specified down at the bottom, and I don't want you to stress about that exact charge, okay, that number. Okay, don't worry about that. I'm not asking you to memorize that, and you won't be tested on that, at least through any of my classes. Okay, but what that charge represents is now the magnitude of the charge on our electron, which is kind of neat. The more interesting thing to me is how do you determine the exact charge on an electron? It's this tiny, tiny particle that when we actually look at its mass, it's so tiny we argue it doesn't exist as a mass. How can we actually isolate it to be able to determine the charge? And that's where we get the oil drop experiment. And so what you're seeing in that picture in the middle is the oil drop experiment. And so what they went through and did is they took a puffer. Women would potentially use these to spray perfume. You might even, I think my daughter has one to squirt glitter all over her face because she's in that stage yet. So it would puff out small particles and create an aerosol, just like a squirt gun or a mister. So those particles now fly out, and then they would, by gravity, fall down. So because they have a mass, we could then calculate how fast they would fall, and we would know something about the mass of the particle based off of the speed at which it was falling, and we could calculate all that fun stuff. Okay, but that doesn't bring in charge yet. So what they went through and did is said, well, if I can find one particle, I can put an electric field near it, because I know when I spray this, it creates a static charge. There's charge associated with these particles. If I can get an electric field near it, I can then start to modulate that field to cause it to levitate. So what we do effectively with our maglev trains. Don't quote me on that, I'm just guessing. So what they went through and did this little spray, but it would be impossible to pick out a single particle in this field of spray. So what they did is they did a spray, and then they had at the bottom of their container a tiny little hole. That hole was so small that only really one drop would be able to fall in. And since it can only fall in that one space, they can set up a microscope at the other end to focus at that one point. So now what they do is they spray, one person's looking at the microscope, sees the drop start to fall through. I see a drop. But we got to make sure that that drop levitates. So how does it levitate? That's the electric field. So we now have a uniform electric field between that. And so you very quickly have to control a dial to control the amount of electric current moving through so that the dot ceases to fall and will actually levitate and stay stationary. You now have two forces acting on it. You have the levitational force of our electric field, and you have the gravitational force downwards from gravity. You can then use that to determine what the actual charge is on the electron. Size of the particle you can measure and get mass, it's absolutely amazing. But the amount of detail that had to go in to watch and be patient enough for this is just insane and very, very, very cool. Okay? So that, I think, is worth discussing in and of itself. The next part that I also think is worth discussing and that you should be aware of is that when we talk about this experiment, Millikan got credit for all this. Fletcher was the one that did all the work. So Millikan was what's known as the primary investigator, the PI. Fletcher was a graduate student in his lab, and as a graduate student had decided that he wanted to do this experiment, and Millikan said, run with it, go with it, see what you can come up with. So Millikan provided both the kind of financial wherewithal and the backboard to support Fletcher in his experiments. Fletcher then designed all the experiments, ran through all the experiments, and then would push that data to Millikan. Millikan would then organize all that data and then publish it. Who gets credit for this? The person that did the work or the person that wrote it up? And this is kind of a sneaky underbelly within science, is that it's usually the person that writes it up, the primary investigator. They're the one that usually get the most credit. So Millikan got a Nobel Prize for this. Fletcher really didn't get any credit as far as the Nobel Prize went. And when you go, or they've gone through and talked to him, he doesn't really feel bitter about it. He just acknowledges that that's the state of affairs of what science is. Okay? What he gets out of it is effectively a guaranteed job. So as soon as he's finished his PhD, and that's all published and worked on, he can then go in to become a professor or go into industry, and he can go wherever he wants, because the field acknowledges that he was a primary contributor behind it. So, give and take within science. Sometimes we got to be a little bit careful and be aware of what we're moving into. Now to more model stuff. So Rutherford is another scientist that comes along. Actually, before we do Rutherford, so within the Millikan-Fletcher experiment, some things that I want you to be aware of. I want you to remember Millikan's name. I want you to remember Fletcher's name. And I want you to remember that they designed together the oil drop experiment and were able to calculate the charge on an electron. That's 4 things. I don't care what the charge is. I just care that you know that they were the ones responsible for doing it. Millikan, Fletcher, oil drop, charge on electron. After that, we can now move to Rutherford and a new model of the atom. I used to like to spin this that Rutherford thought Thomson was entirely incorrect and his theory was bogus. And so what we're seeing up here is the plum pudding model. Turns out that was probably entirely a false statement because Rutherford was a student of Thomson. So what you'll kind of notice when you dig through some of the history behind all of this is that all of these scientists knew each other and talked to each other a lot, regardless of where they were in the world. So back to Rutherford. Rutherford wanted to prove or disprove Thomson's plum pudding model of the atom. So to do that, he designed this particular experiment where he took alpha particles, and alpha particles will be important here in a second. So alpha particles are, we'll just call it a mass of 2. Okay, remember we said our proton was a single mass. Actually, we didn't define that. We'll just say it's 1. So our alpha particle, I should have looked that up. I believe it's actually 4 times the mass of a single proton. Okay, so it's fairly massive. It is also positively charged. Okay, so those are kind of important things to know. These alpha particles are a form of nuclear radiation, which comes from different radioactive elements. So if you heard of booms, those are radioactive elements. Depending on how they decay, they can be boom or they can be a little bit more mild. And so what Rutherford was able to do was to take these alpha particles and aim them at a sheet of gold foil. Okay, so gold foil we can get real thin, so we're assuming an atom or 2 thick, so very, very tiny thin film. The way he described it was effectively toilet paper. And if we fire this alpha particle beam at it, what are your alpha particles going to do? Well, they're going to pass straight through. They're 4 times the mass of a positive thing. We're just looking at a sea of positives here, and then we have our electrons chilling in there. So if anything, these might hit and ricochet a little bit, but we're not going to see much movement off of that lateral direction. So the way he described this is we're taking a shotgun and aiming it at toilet paper. Okay, what's our prediction? It goes straight through. That's what it does. And if that's the case, then what do we see? Well, what we end up seeing is that we've proved Thomson's model. That's pretty straightforward. Except that's not what he saw. Okay, what he saw instead is what we're seeing down below. Every so often, you'd get these weird deflections and significant deflections. So down here, those are relatively minor deflections, not a big deal. But these ones off to the side, those are pretty massive deflections. Okay? And then every so often, super rarely, but it did happen, what you would note is an almost direct bounce back. That makes no sense. Okay? If the positive particle flew through and hit an electron, it would stick to the electron. Okay? It's a sea of positives. There's nothing for it to hit. Why is it bouncing back? Back to a shotgun example, we take a shotgun and shoot it at a piece of toilet paper, and the pellets bounce back. That's flipping crazy. Okay, and so what that suggests is that Thomson's model does not work. Okay, that's the big key here. And some of the other secondary pieces associated with it, that these positives, because remember the alpha particles are positive, what it must be impacting here at that impact site, that impact needs to be something that is also positive. It needs to be something positive, and it needs to be something massive. Okay? Larger than this 4 value. Okay? That's a pretty big deal, and that's going to be a big shift in our atomic theory. Before we get into that, let's take a sidebar and take a look back to what these alpha particles are. Okay, so alpha particles are not an easy thing to obtain. Like I said, they're radioactive. And as you might guess, working with radioactive species a lot could lead to cancer and all sorts of death and bad things. So it's kind of hard to get a hold of these things. So where did they come from? Well, they ultimately came from, did I get her name on it? Oh, I didn't even put her name on it. It's horrible. Madame Curie. So Curie is a fascinating woman, and I would argue that everybody should go read up on her. And Madame Curie was most known for her chemical purification techniques. So she was able to isolate both radium and polonium. I'm a little panicked about that because I think I got them wrong, but I think that maybe that's right. So she isolated radium and polonium. And what's special about both radium and polonium is that they are radioactive. And so when they fall apart through their radioactive decay, they emit alpha particles. The problem is in that process of falling apart, they change their identity and the sample itself becomes very, very, very impure. And if you have something that's impure, it becomes really hard to know how useful it is. So this is where Madame Curie's chemical purification techniques become so valuable because she's able to isolate and pull this out so that Rutherford can then use these. So he didn't have a source of alpha particles he could purify. He actually requested it from her. And so she sent a sample across, allowing him to go through and run his experiments. So how important are these discoveries from Madame Curie's? I would argue phenomenal chemist, phenomenal chemist, did it again, chemist, as well as just a general scientist. Very good at taking notes, very methodical, very good chemical preparation technique to actually isolate things. How valued was it? She won 2 Nobel Prizes. Okay, so that's pretty important. There's 5 people in the history of Nobel Prize that have won 2 Nobel Prizes, and she's one of them. She's the only woman, I think, on that list. Right? She won one in chemistry and one in physics. Okay? The chemistry was for her chemical isolation, and the one in physics was for the study of radiation. So really, really neat. What makes this even more powerful is we're talking about early 1900s, and if we think through the rights that women had, you could argue sometimes still have, depending on where you're at, it was pretty limited. So for her to be able to do these experiments and run these processes in a world that didn't even allow her to vote is pretty phenomenally impressive. So very strong-willed woman, amazing. Highly recommend that you read up on her. Yeah, so I'm going to leave it at that, and we'll continue on because I won't stop talking about it, and I'll probably make a whole bunch of stuff up. So let's just go ahead and move on. So let's clear our ink, and let's go ahead and move on to the next aspect, and that's our theory coming out of Rutherford. So Rutherford said that we had to have this super solid, massive thing, and it had to be positive. So we put all of the positive particles that Thomson had created, or defined, our protons, and put them all in a super dense space. Since they're now in a super centralized space, we need a new name for it, and that's where we get the nucleus, or nuclear, the center of our atom. You'll note that this picture isn't just red, it's also blue. Right? Well, why would we have red and blue within this? He's not saying electrons are going in there, but what he's noting is that those positively charged particles, if they got near each other, would repel away. This is the north and north end of a magnet. Okay? So if I'm going to have a nucleus where I put all the positive charge there, there's probably something else there holding the positives in. And that's now where he defines kind of an extra particle that needs to go into our nucleus in our subatomic world. Okay? Last thing before we move on, to give you an idea of scale, the atom has a diameter, you can read the numbers, super, super tiny, and the nucleus has a diameter of about 10 to the negative 13. So we're like, negative 8, negative 13, how big a deal can that be? This is the problem with powers of 10, which we'll get into later on. If the atom were the size of the superdome, so our 13, the nucleus would be a marble inside the superdome. So we're talking a football stadium, marble inside it is our nucleus. So very, very compacted, very small size for our nucleus. The rest of the atom's size, okay, and size is a gray area that we'll deal with later on in this semester, is due to our electron cloud around it. So what does that set us up with? We've got Rutherford's model of the atom. We have to have neutral particles in addition to the protons. Why did he theorize this? Hopefully you remembered that the protons would repel away from each other. And then we have these neutrons, or these neutral particles. Those neutrons were experimentally discovered by James Chadwick. Don't stress about Chadwick. It's not a bad name to know. And a neutron is about the same mass as a proton, but it has no charge. So equal mass, but no charge. The fun fact about Chadwick is that Chadwick was actually a student of Rutherford's as well. So, like I said, they're all kind of tied to each other as they built this research out. A little suspicious there's something in that white space, but there wasn't, so we won't worry about it. Which then takes us to our subatomic particles. This red boxed table at the bottom, you need to know that, right? You need to know what an electron is, a proton, a neutron. You need to know what those words mean. You need to know the symbols that are associated with them. The symbols are usually pretty straightforward. You need to know where they're located, their charge, their mass. All of those things contribute to our understanding of the subatomic particles. And as we navigate further through the semester, what we're going to end up doing is applying that concept to other situations. So if you don't have this memorized, you won't be able to apply it later on. We need to be able to do both those pieces. So please spend the time to go through and memorize it. One thing that I'll go through and simplify is that if we look at the mass for an electron, it's 1 over 1,836, which is an insanely tiny number. Relative, it's about 0. So if you memorize the mass of an electron as 0, that's going to be much more effective than memorizing it as that fraction. Okay? Which we will go ahead and call that the end of this lecture. I apologize. I thought I was going to talk a little bit more. So with that, we will go ahead and call it. Thank you for watching so far. I hope you have a great rest of the day, and we'll catch you on the next one. Bye-bye.